Hey Pre-16 class, here is a quick video going over the last 3 graphing examples from class K. Actually, this isn't the one I want to start with. This is. So again, we're looking at the reflections, the shifts, and the dilations, all the stretching and compressing. So here I see a 2 inside the square root function, so I know I'm going to compress by a factor of 2. So if the normal square root function looks something like this, where you've got the point like 1, 1. This is going to squeeze it in by a factor of 2. So this is the square root of x. And if you look at the notes, you'll see that I've kind of drawn them all in the same thing. I'm not going to do that here. I'm just going to draw them all kind of separately. So I'm going to try to be a little more precise. So we do the square root of 2x. Everything gets scrunched that way. So instead of being in the point 1, 1, if I'm doing the square root of 2x, if x is 1/2, 2 times 1/2 is 1, square root of 1 is 1. So point 1/2, 1. And if x is 2, 2 times 2 is 4, square root of 4 is 2. And if x is 9 over 2, which is 4 1/2, right there, the y value is going to be 3. So this gets kind of scrunched. Right, I'm pushing all these values back that way. The minus sign in front is going to flip it vertically. The minus 3 after that's going to shift it down 3. So we're going to get this flipped over, going that way, and then move down 3. I think we can do both those at once. I still need to shift it down 3, so I need a little more space. Again, your graph doesn't have to be perfect. I'm just trying to show you guys what is exactly happening here. So flip it over, it's going down like that, and then down 3. So it's going to start at 0, -3. And then I'm going to have the point 1/2 comma -1, and then 2 comma negative, 1/2 -4, 2 -5. So look like this. It doesn't flatten out. It still keeps going more and more negative. It's kind of hard to draw it when you're looking like this. But it does keep going down and to the right. So that's that, right? We scrunched it horizontally, we flipped it vertically, and we shifted it down. Let's look at the next one. The next one has kind of an interesting little thing. So you might look at this one and think at the beginning it's going to shift to the right by 1. But it actually doesn't shift to the right by 1. So when you have a horizontal dilation, meaning a stretch or compression, and a horizontal shift, you have to kind of deal with the stretch part first, meaning we need to kind of factor out this 1/3. So I'm going to write this as 1/3 times x minus 3 minus 4. Because if you distribute the 1/3, right, you're going to get back this. So this is actually going to shift 3 to the right. You could also kind of think of it as shifting 1 to the right and then kind of horizontally stretching it by a factor of 3. That's another way I guess you could do it, although it seems kind of weird to me to do it that way. Yeah, it seems like, I'm trying to think about it now, like if you shifted the absolute value 1 to the right, it would look like this. Well, that's 1, 0. And then you have to kind of stretch it by a factor of 3, but you're stretching it from the middle, which just seems, right, it seems weird to kind of stretch from here by a factor of 3. I mean, it would work. This stretches to right, so this point here, 0, 1 still stays the same, but this point here, 1, 0 stretches 3 to the right, and you get that there. It's going to look kind of stupid. So I guess you don't have to do it this way. You can say, here's my y equal to the absolute value of x minus 1, shifted 1 to the right, and then here is my y equals the absolute value of 1/3 times x minus 1. I took my shifted 1 to the right and I stretched that by a factor of 3. So the 1 got multiplied by 3 and became 3, 0. this 0, 1 got multiplied by 3, but the 0 is the part, right? The x part when you're stretching it horizontally is the part that's getting multiplied by 3, so it's still 0, 1. It actually kind of works. And then we shift it down by 4. So I'll try and draw the final graph up here. I'm just going to move this point 3, 0 down to 3, negative 4. Let me go ahead and erase this so I have the room. So this point 3, 0 is going to move down to 3, negative 4. Right, I shifted 3 to the right and 4 down. And then this point 0, 1, you could also shift 4 down to 0, negative 3. So it's going to look like this. And then like that. Eventually it would cross the x-axis, it's just going to take a while to get there. Yeah, and if you look at the graphs I drew in the notes, you can definitely see that as well. Like it's going to take a while to get up that high, but it does eventually get there. Yeah, so our absolute value function, which normally would look like this, shifted 3 to the right, or I should say shifted 1 to the right, then stretched by a factor of 3 horizontally, then shifted down 4. Let's look at the very last one, which I think is a little easier than this, at least conceptually, but harder for me personally to graph. So the last one here is going to be f of x equal to 1/2 times x minus 2 cubed. So this is your normal, I suppose I should have said for the last one, right? The original graph was the parent function was the absolute value of x. I guess I did say that. Here, the parent graph is x cubed, which you all know I'm not good at drawing. Looks kind of like this. So there's x cubed. We're going to shift it 2 to the right. So, yeah, I feel like I'm just terrible at drawing this one. So let's shift it 2 to the right. So normally I'd have the points -1, -1, 0, 0, and 1, 1. I'm going to shift that all 2 to the right. So instead of having 0, 0, I'm going to have 2, 0. Instead of having 1, 1, I'm going to have 3, 1. And instead of having -1, 1, I'm going to have +1, -1. So those are my 3 points. So it's going to look like this. Sure. And the reason I'm drawing so much of it on the left here is so that you guys can see that even though it gets very steep, it does have a y-intercept, right? It definitely crosses the y-axis. It doesn't have a vertical asymptote there. So this would be y equal to x minus 2 cubed. And then multiplying by 1/2 is going to scrunch it vertically by a factor of 1/2. So instead of getting, the point like 1, 1, we're gonna smoosh that. We're gonna smush it down by a factor of 2. So it's gonna go down to right there. This one's gonna get smushed up by a factor of 2. And so you're always compressing towards the x-axis if it's vertically, or towards the y-axis if it's horizontally. So, yeah, I'm always running out of room. There's never enough room. So let's start graphing the actual function that we want to graph here. So I still have the point 2, 0, but now instead of 1, -1, I'm going to have 1, -1/2. Instead of having the point 3, 1, I have 3, 1/2, right? All the y values got crushed in half. And then I suppose you could also look at the y-intercept here just for fun. The y-intercept here, if x is 0, here it would be 0, -8, right? If x is 0, y equals -8. So here, if x is 0, y should be half of that, -4. So it's going to look like that. Well, it's not too shabby. I know it looks kind of the same. When you have these really kind of long vertical functions, it's kind of hard to really see the effects of a vertical compression. What I would recommend to everyone is Desmos is a tool. You can use it. I would maybe explore how the transformations, like step by step, like I would graph with Desmos first x cubed, and then x minus 2 cubed, and then 1/2 times x minus 2 cubed, to kind of really see how the transformations really shape the graph. That's all I've got. Those are those last 3 examples. I hope you find them helpful. I have office hours tomorrow at 10 o'clock. Come on by.